In this video, we look at the derivatives of the trig functions. Earlier, we had observed that the derivative, or the instantaneous rate of change, of sine x at a particular point was the cosine of that x value. So the derivative of the sine function is the cosine function. We also discovered that the derivative of cosine was minus sine. All of this required, of course, that we're using radians as our natural angle measurement. We do not want to use degrees. If we use degrees instead, the derivative of sine of x is pi divided by 180 times cosine of x. Trust me, this would make all our computations significantly worse. As long as we stick to radians, the derivative of sine is cosine. The derivative of cosine is minus sine. The fundamental trig functions are ratios of sine and cosine, and so the quotient rule will give us the derivatives of the other fundamental trig functions. Given the quotient rule, we can easily, for example, find the derivative of tangent. Let's write the tangent as sine over cosine, and then by the quotient rule, the derivative of sine over cosine will have a cosine squared in the denominator. The numerator will be the derivative of sine times cosine minus sine times the derivative of cosine. In other words, cosine squared plus sine squared all over cosine squared. Now you might look at that numerator and recognize it as part of an identity. By the Pythagorean theorem of trig, the cosine squared of x plus the sine squared of x is 1. So the derivative is 1 over cosine squared, or if we wish, we can think of the derivative of tangent as secant squared. Using the quotient rule and writing tangent as a quotient, and using the Pythagorean theorem, we can get the derivative of tangent as secant squared. Using old traditions about powers of trig functions, we'll put the 2 over the secant, so the derivative is secant superscript 2x. We can do the same thing with the cotangent. We can write the cotangent as cosine over sine and work through the quotient rule. It's a good exercise to do, and the answer will be minus cosecant squared of x. The derivative of the secant function also comes from the quotient rule. If I think of the secant function as 1 divided by cosine, then by the quotient rule, we will put a cosine squared in the denominator. The derivative of 1 is 0, so we have 0 times cosine x minus, we'll write down 1 times the derivative of cosine. The derivative of cosine is minus sine, and so we have 0 times cosine plus sine, or just sine in the numerator. So we have sine over cosine squared. We can rewrite this, breaking up the two cosines in the bottom so that we have sine over cosine times 1 over cosine. This is going to be the standard answer, tangent x secant x. That's the derivative of secant. We can do the exact same thing with cosecant. The cosecant is the reciprocal of sine. The quotient rule, almost identical work, will give us the negative of cotangent x. So here are the results we've got so far. The derivative of sine is cosine. The derivative of tangent is secant squared. The derivative of secant is secant x tangent x. We did the last two using the quotient rule. And we also know that the derivative of cosine is minus sine. The derivative of cotangent is minus cosecant squared, and the derivative of cosecant is minus cosecant cotangent. There's a pattern here. If you know the first three, I remember the first three, then the bottom three can be derived from the first ones, because instead of differentiating the original trig function up here on top in this pattern, we're taking the derivatives of the complementary function. These are cosine, cotangent, cosecant, and we're getting negatives of the complementary functions. Let me take a moment to explain that. Given an angle theta, the angle we need to complete a right angle is called the complement of theta, or the complementary angle. The complementary angle is 90 degrees minus theta, or in radians, pi over 2 minus theta. If I draw a unit circle and put a triangle in it, here's the central angle theta on the left of the triangle. Up in the upper right is the complementary angle. The sine of theta will be the cosine of the complement, and vice versa. The term complementary will explain the syllable co in the terms cosine, cotangent, cosecant. The cosine of an angle, theta, is the sine of the complement. The cosine is the abbreviation. What it means is sine of complement. Cosine is sine of complement. If the sine of this angle is the opposite over the hypotenuse, and the cosine is the adjacent over the hypotenuse, then the sine of the complementary angle, would be the angle opposite to it A divided by the hypotenuse. The sine of the complement is the complement of the sine. Same way, cotangent will stand for the tangent of the complement. Cosecant will stand for the secant of the complement. Now, earlier we derived the basic derivative rule. Sine x is derivative of cosine, derivative of tangent, secant squared, derivative of secant is secant tangent. The remaining three derivatives can be described as follows. Take the derivative of a complementary trig function like cosine or cotangent or cosecant is the negative of the complement of the derivative. Roughly speaking, the derivative of co-f is minus co-derivative of f. That gives this table the derivatives of complementary functions. Again, derivative of sine is cosine, derivative of tangent is secant squared, derivative of secant is secant tangent. These are the three trig derivatives I remember. And then if instead of sine, I want to do cosine, then I take the negative of the complementary answer. A moment ago, we had sine is derivative of cosine. The complements of sine is cosine. The complement of cosine is sine. So the derivative of cosine is minus sine. The derivative of cotangent is minus cosecant squared. The derivative of cosecant is minus cosecant cotangent. Now that we understand the product and quotient rules and the derivatives of the trig functions, it's time to go on to the chain rule. That is next.